downwards. So let me just take 1 minute to summarize what's going to be important. First of all, this is this idea of pneumatic symmetry. Special direction, but up and down are the same. Pneumatic liquid crystals are like that. And the flow fields around active particles are like that. That's because active particles are self-propelled, and as a result, there's no net force. And a corollary of that, a consequence of that, is that they pump fluid out from their ends and pulling it in from the sides. That's called an extensile swimmer. Or you can have them doing it the other way around, pulling fluid in from the ends and pumping it out from the sides, and that's called a contractile swimmer. The other really important thing is this idea of topological defects, places where the pneumatic order goes wrong in a big way. We're going to be in 2 dimensions, because that's pretty much where all the experiments are. And we're going to worry about topological defects mostly, which either look like this, with a topological charge plus a half. So this is a plus a half defect. And then the minus a half defects look like that. And those are the most common ones in 2-dimensional pneumatics. So what I want to move on to today is trying to understand this stuff, active turbulence. If you have a lot of active particles together, and in particular, these are tiny bacteria, swimming bacteria, then you end up with something which looks like turbulence. You get loads of vorticity, okay? Lots of swirly flows in this system. That's vorticity. And it looks very chaotic. But we're definitely at low Reynolds number here. So why can you get these chaotic flows at such low Reynolds number? So I thought what I'm going to just do now is tell you about another experimental system. So we're going to stop the development just for a minute to talk about another experimental system which shows this active turbulence and which has been very important in the development of this subject. And what that is a mixture of microtubules and molecular motors. So here we are. These are, well, we saw this last time. Let's play it again. The cell lays down microtubules, and then to transport things, it has molecular motors, which will appear in a minute, which walk along the microtubules. Now, about 5 years ago, Zvonimir Dodzik at Brandeis was very clever, and he managed to isolate microtubules. So you just have microtubules here. And then he added to those some molecular motors, but they were special molecular motors because they had 2 heads. So they could attach to both microtubules, to 2 microtubules at the same time, and form a bridge between the microtubules. He got these things out of cows. If you're vegetarian, don't listen at this point. But he got these things out of the brains of cows from the abattoir in Boston. Okay, so he's got these microtubules and the molecular motors. And then he wanted to make a dense suspension of the microtubules, and so he added PEG. And this is just something which pushes them together. So you end up with lots of these microtubules very close to each other with 2-headed motors between them. Now, these motors walk in a specified direction along the microtubules. So a given motor will only walk in one direction. So if a motor bridges 2 microtubules and both ends move in the same direction, absolutely nothing is going to happen. But if a motor bridges 2 microtubules and this end is moving upwards and that end is moving downwards, it will push the microtubules relative to each other, and it will tend to separate them out, really, that all the ones going downwards will form a clump down here, and all the ones going upwards will form a clump up there. You get something called polarity sorting. So what happens is that these things tend to form long, thin clusters of microtubules. So now let's just look at the dynamics of that. They take this stuff and they put it on an interface in 2 dimensions. So it's a 2-dimensional system. And it's going to be moving because of the microtubules, and it looks, sorry, because of the motors, and it looks like this. These sort of white stringy things are these bundles of microtubules. They're being driven by molecular motors, and again, you see a pretty chaotic state. But there is some sort of structure in there, right? This thing here looks a bit like that +1/2 topological defect, and this thing here looks a bit like the -1/2 topological defect. And it's turned out to be the best experimental system to try and match to the theories, this microtubule molecular motor system. Okay, so we want to do a theory now of this active turbulence. And it turns out that the equations you need are very similar to the equations for liquid crystals. I'm going to work on a hydrodynamic level, on a continuum level. What that means is it's like the Navier-Stokes equations for a simple fluid, but we now need to write down the equations for a more complicated fluid, for this active fluid. And it turns out that what you need is to start with the equations of liquid crystals. That's because the flow fields have pneumatic symmetry, so you need to start with something with pneumatic symmetry. So we need to write down the continuum equations for liquid crystals, and those are very well known, but they're also a bit hard, okay? So I'm going to do them, but if you don't like the next 5 slides, it really doesn't matter. You can forget about them when they've gone through. But the important thing is that you just then have to add one more thing to make them active, and this is extra thing that we're adding, which will be important, and will have all the physics in it. So the next 5 slides are for the mathematicians among you who like nice big equations, okay? And then we'll just come to the physics at the end, and don't worry about the next bit. Okay, so continuum equations for liquid crystals. So Navier-Stokes-like equations, but instead for this fluid made up of these long, thin molecules. So first of all, you need an equation for the order parameter Q. This was the order parameter telling me about the order, and it tells me how the order is moved around the system. So this Q is moved by the flow. This is the usual d by dt plus u dot grad, the convective derivative, like you always see in the Navier-Stokes. The order is moved around the system. This term is a rotational term. Looks horrible, but physics-wise, it's all right. What it does is it just says, my molecules are like this, so any sort of shear flow is going to turn them. And I need to make sure that's in the equations. And you put that in the equations like this, where this E thing is the extensional flow, du by dx, dux by dy plus duy by dx. And this thing here is the rotational flow. And then this term here says, my system relaxes to a minimum of a free energy. Here's the same free energy that we had yesterday. Okay? Expansion in the order parameter. If you're not pushing it, it will just relax to a pneumatic state, which isn't moving. So that's the equation for the order parameter. Then we need an equation for the flow, and that looks, if you write it like this, exactly the same as the normal Navier-Stokes equation for the flow, dt plus u dot grad du, that's the inertial terms. And then this side, I have the derivative of the stress. And in Navier-Stokes, the stress is just related to the velocity gradient tensor. Here's the viscosity. It's just the viscous terms. The extra thing you have in here is the most horrible thing, which people understand, but it's pretty horrible, right? It's got this molecular field, df by dq, and these q's in. But physically, what it's doing is just that if I have a molecule and it decides to move like this and turn, it's going to induce flows. It's going to make the system flow. And that's putting that in. And you add it in the stress. Okay, the stress here comes under a derivative. So we understand how to write down these equations, and when you've been staring at them for about 5 years, you sort of work out what each bit is. And you can solve them. We solve them using Lattice-Boltzmann for the flow bit and finite differences for the Q bit. So that's just a summary of the continuum equations of liquid crystal hydrodynamics. If now I add active particles, swimmers, to my fluid, what's going to happen is that they themselves are going to create flow fields, and I have to add in the effect of that. And it turns out to be very easy to add in the effect of those flow fields. And I'm going to argue on grounds of symmetry. I mean, actually doing it mathematically is pretty tricky and approximate, but it turns out that all you have to do is you have to add, oh gosh, oh, there it is, this extra term, this active stress, okay? And the active stress, which takes account of the flow fields produced by the swimmers, is equal to zeta. That's just a number which says how many swimmers there are, how strong the flow field is. This is called the activity, and it's proportional to Q. And that makes sense. That's why I was on about these things having a nematic flow field. That means that when you add this extra term, it's proportional to Q. It has to have this symmetry. So it makes sense it looks like that, but I'm just telling you it's not a proof, but it makes sense that this extra stress is proportional to Q. And look where it comes. It comes in here. It's an extra term in the stress, and it's under a derivative. So what that means is that any time there is a gradient in Q, this derivative will have a non-zero value, and you will have an extra force on the fluid. OK, I'm now going to say that again in words. This is the important bit, so don't worry if you didn't like the last bit, OK? Because you've got these active particles swimming around in your fluid, you have an extra stress. And what this stress does is that any time the nematic order is mucked up, any time you don't have perfect nematic order, you get an additional stress, an additional force on the fluid. And of course, if you've got an extra force, you induce flow. Anytime the nematic order has any sort of deviations in it, anything that's not perfectly nematic will give you a flow field. Let's see how that works in pictures. Here's my perfect nematic, all nice and lined up. And there's going to be a little fluctuation. And the little fluctuation is going to maybe say, do this to the nematic order. This is a little bend in stability. Gradients in the nematic order, right? These are gradients. It changes from place to place, induce flows. And you can work it out. The flows are like this. The flows up there are like that. And the flows down here are like that. So what's going to happen? Well, this thing's going to get more mucked up, yeah? It's going to be pushed like this. And so the nematic state is going to be completely unstable because of these active flows. If you want the maths words for the same thing, if you do linear stability analysis, asking how the active term affects the nematic state is unstable to these active stresses. You can't have a perfect active nematic. It will just blow up. OK? So what do you get instead? What you get instead is active turbulence. OK? So we can't look at active turbulence using linear stability analysis. We know the stable state is the nematic state is unstable, and so you're going to cross over to something else, but you don't know what it is from the maths, but you can solve the equations numerically. And so let's solve the equations numerically and see what this active turbulence looks like. So what I'm doing is I'm taking those horrible equations I showed you with the active term. I'm solving it numerically. Okay? This is the experiment. I can't actually remember whether this is an experiment or a simulation, but it doesn't matter because they look pretty much identical. And what I'm plotting here is the vorticity field. Vorticity is the amount the fluid goes like this. It's the curl of the velocity. It tells you about vortices, about the fluid going round and round. If the thing's red, that's anti-clockwise vortices. And if it's blue, it's clockwise vortices. And the sort of length scale of these vortices is maybe about 5 swimmer lengths. So you're getting collective motion in these systems. The swimmers are somehow organizing themselves into local transient vortices. Let's look at the, there it is again. Okay, let's sort of look a little bit closer about what's going on here. This is my vorticity field. The black lines are the velocity. You can see them going round and round the vortices here. Okay. Let's just look and magnify that bit there, because I'd actually like to see the pneumatic director, or if you like, the individual swimmers. Okay, so this is now taking bits and enlarging them. And these little lines are my pneumatic director, or if you like, my individual swimmers. And you can see that what's happening is that here I have a bend in the order, definite gradients in the pneumatic order there. That's giving me stresses, and that's what's driving these flows. And then the flows muck up the order somewhere else, more stresses drive more flows, and you get this turbulent-like state. Okay? That's the hard bit. Anybody got any questions? Anybody? Questions? Yeah, go on.
If you don't have any pattern, like these figures that you are showing, it's possible to use these equations to predict, I don't know, because maybe you can have a very heterogeneous system with many other kind of particles, and maybe you cannot have a specific pattern like that. I was imagining if you can apply really these equations.
It has to be a pneumatic. Okay, it has to be long, thin. It works for a liquid crystal, which has long, thin molecules. It would work for colloids, which are long and thin. And it works for these swimmers, both because they're long and thin, but also because the flow fields they produce have this pneumatic symmetry. Yeah. So it depends on that. Good question. Anybody else got?
Why doesn't it matter if the active matter is small, like bacteria, or microtubules?
Microtubules are still micron length scales, so you're sort of the same length scale, but they're much longer and thinner. It seems to still work because you're coarse graining out that detail, but people have worried a bit about, you know, the effect of the long thinness. It doesn't really matter on this scale, yeah. It doesn't work for really big things like birds, we think. Okay. Right, so it's a pneumatic. And I was going on about pneumatics having topological defects. Yeah? Yes?
Since you said about birds, did you try it for fish?
It's not going to work for fish because the inertia, they're bigger, so the inertia is important. No one's really seen topological defects in fish. And quite honestly, I don't think anyone's got them swimming in 2 dimensions. You have this 3rd dimension with fish, yeah. I don't understand fish at all. Yeah. Yeah. Okay, so if we've got a passive pneumatic, a pneumatic without activity, plus and minus defects, okay, what do? They anneal out. They move towards each other, and they annihilate to give you back the very nice pneumatic order. So in a normal molecular liquid crystal, unless they get stuck, topological defects will gradually destroy each other in pairs to go back to beautiful pneumatic order. This is a pneumatic, right here, my directive field. Let's have a look at the topological defects in this system. So the red dots are the +1/2 defects, and the minus dots are the blue dots are the -1/2 defects. Okay, this is what they look like. Let's just watch them. This is from solving the equations. Okay, so what are they doing? I mean, you can see them disappearing there. But by the end, they don't seem to be any less. So did anyone see any popping out? Yep. Let's try it again. What is weird in this system, what's very different, is you get them destroying each other in pairs. I still can't find them in the right way. Okay? Those are going to do it. Yep. But if you look up here, I'm going to do it there. They also get created in pairs. And then they move away from each other. Okay? And that's what's different about these active systems. Topological defects are destroyed, just like the passive systems. But also, you can get them being created. And you always have to have them created as a plus and minus pair to preserve topological charge. So why is that okay? Well, it's okay because these are active systems. They're taking energy from their surroundings, and that gives them the energy to make these topological defects. Why don't the defects just appear and then immediately just annihilate each other? I mean, normally, a little fluctuation will give you a pair of defects in an ordinary liquid crystal, but then they just annihilate straight away. And if we look at this again, you'll see that what happens is if they're created, they immediately move away from each other. I think the ones up there do it. Let's have a look again, because this is sort of the important bit, really. It's going to be, and watch them move away from each other when they're formed. Yeah? And that's because these +1/2 ones move. They're self-motile. And we understand why they're self-motile, because we've said, right, we've said that if there's any sort of places where the order is wrong, any sort of derivative in the order, any sort of, what's it called, but, you know, deviations in the pneumatic order, which there obviously are there, you get stresses. And what this stress does is it moves this. So a +1/2 defect is self-motile. This guy here, also you get gradients in the order, and so you're going to get stresses, but just by symmetry, the stresses are going to tend to balance each other out. So these chaps tend to stay put. We can look at the flow field around the defects. Okay? This is a +1/2. It's moving, it moves in this direction, and as it moves, it sets up a flow field like that. This one here is a -1/2, and you can see you get this 6-fold symmetry in the flow field. You get 6 vortices around it. So it produces a flow, but it doesn't go anywhere, and it reflects the 3-fold symmetry of the defect. And remember those pictures, because we're going to see them again when I show you some experiments which give you that sort of flow field. So can we see them in the experiments? So let's have a look again at this system of microtubules being propelled by molecular motors. Okay. It's really hard to see when they're moving quickly until you're used to it. But I've got a still, I think, next. You can sort of see you're getting shapes appearing, yeah? When it stops, that looks like a -1/2. We got this one here, looks like a +1/2. And, whoops, here what you can see is what happens is that these things tend to bend. The motors tend to make them bend, and then what happens is that the bend really corresponds to this bit here being a +1/2 defect, and this bit here being a -1/2 defect. And then as the bending continues, it's like having the plus moving away from the minus stays put, the plus moves. And you can measure things like the velocity-velocity correlation function, either of the defects or of the microtubules, and you can measure them in the simulations. And I didn't put the graphs up, but they match beautifully. So it's not just looking at it. You can actually measure things and see that the two simulations, the theories, and what's happening here agrees with each other. I think I've got a couple more pictures. These are more recent experiments. These are from Francesc Sagres's group in Spain. And what this tells you is shows you is the original instability. So what they did is that to line up the microtubules, okay, they did it in a very technical way. They put a straw in the thing and sucked. And therefore, the microtubules all lined up like this. Okay? And I said the pneumatic state's unstable, so when they stop sucking, you should get an instability forming. Does it quickly, so we'll do it twice. Okay, so they get the things lined up when it's quite hard to see them, and then here's the instability. You can see them starting to bend there. Okay? And then it just gets a mess because everything's becoming super unstable. Let me play that again. Okay, so this is when they're lined up and you can't really see them. But as they start to bend, you can start seeing them bending. So that's the initial instability where you're going from a pneumatic state to this active turbulence. And then, again, this shows a part of that. Here they're lined up, and you do that. And you get these bends and the topological defects forming. Oh, okay, yes. And then I put this one in because this was actually quite an early experiment, and it's very cute. This is by the Dogic group. So what this is rather than having a flat two-dimensional layer of this active stuff, they put it on the outside of a vesicle. And so it's doing active turbulence on the outside of a vesicle. And then if you put the vesicle on a surface, the forces from the active turbulence cause it to move around on the surface. Those of you that were in my class this morning, if you look very carefully, you'll see little spikes there sticking out on the outside of this, like that one. Suddenly get these spikes. Those start at topological defects. So this is a case where topological defects do give you spikes. Okay, are we all, any questions? All right, happy with that? So what I want to talk about next is, we've done those two bits, and in a way that's the punchline, really. These active pneumatics, the important thing about them is the self-propelled topological defects. So what I'm going to talk about now is another set of experiments and theories when we try to understand where you take the active stuff and you confine it. So you put it in a channel. I'm going to really concentrate on putting the active pneumatics in a channel. So we're really in one dimension. Imagine it's on the surface, and then you just confine it like this. So it's like a one-dimensional channel. What happens? Oh, rats. Sorry. I'll put these tomorrow because I forgot I was doing those now. Yeah, we are. OK. So why do we care about active material in confinement? Well, first of all, it's realistic. I'm going to talk a bit more tomorrow about how things are biological systems. Some active systems are biological, and often biological materials are confined. For example, a tumor is an example of a three-dimensional confined active system. The other thing is that, you know, if you actually want to use this stuff as engines, you'd really rather it didn't just sort of wriggle about all over the place. What you'd like to do is have a microfluidic channel, and then these swimmers self-propel themselves down the channel in a nice regular way, and so you can use them to do work. So you'd like to try and stop them doing active turbulence. And maybe confining them is one way to do that. And the punchline of this is that, yes, you can do that, and you can really explain everything in terms of two competing length scales. First of all, you've got a length scale, which is the width of your channel. The width of your channel is going to give you one length scale, yep? Anyone like to tell me what the other length scale might be? What sets the length scale for the active system? Sorry, the microns. It is microns, but what sets that micron length scale? Sorry?
Size of the active particle.
Not really. I mean, that would be a jolly good guess, but remember we're looking at collective behaviors here. What sets the size of the collective behaviors? Correlation length. The correlation of what, though? Correlation of what? Vorticity, yes, that's right. Okay, you've got these vortices, and it's the size of those vortices which sets the length scale. What's going to matter is the size of the vortices compared to the size of the channel. Because if the channel's really big compared to the vortices, you'd expect this active turbulence, but if it's small compared to the vortices, you get something else. So let's try and work out what the something else is. Right, so I'll show you pictures in a minute, but let's just put it together. This is the important axis. When we did this, we hadn't a clue to what to put up there, and I think we still don't. This is the important axis, all right? This we call the activity number. What it is just a ratio of the size of the channel to the size of these active vortices, okay? So what happens is here, nothing happens. If the channel's really, really narrow, the stuff just sits there. Here, you get laminar flow. What that means is it all just flows nicely along the channel like a very simple liquid. In the pink bit, it starts going a bit wriggly. This is something which we called the dancing state, for reasons I'll explain, and then here, wide channel active turbulence. So let's go through that again, but now in pictures. Here I'm plotting the vorticity. Plotting the vorticity as the channel width increases. All right, I know it doesn't look like it increases because we've pushed it down, but the channel width is increasing, or if you like, similarly, the activity is increasing. All right, so here you start off not flowing at all, and then you flow along the channel as laminar flow. Coloring is a bit weird because vorticity looks a bit weird in laminar flow. You can see that the streamlines start being wriggly. And then you get this state here, this state where you get opposing vortices. You get blue vortices which are going around in one direction next to red vortices going around in the other direction. A bit like Rayleigh-Bernard rolls, for those of you that know about fluid mechanics, a line of opposing vortices. And then you get active turbulence. And this makes sense, right? This is when that vortex is just the right size to fit in the channel. So let's look at this special state here. Oh, well, it's a movie, right. You can see the vortices sort of take over from each other. The blue ones win, and then the red ones win. Let's look at this dancing state a bit better, because it really is a very cute state. We called it the Cayley dance for reasons which will become apparent in a minute, okay? And here again, I think I've got a movie. All right, so you get red vortices going around this way and then blue ones going around that way. That always happens in fluids. Vortices are always opposing, so you don't get lots of friction when they're next to each other. And then look what the topological defects do. Let's see if I could do this here. This green topological defect is going round like this. That's a plus a half does this. All right? Then some of the other plus a halves go in the opposite direction. All right? And then the minus a half sits on the walls. So the minus a half sit on the walls. Those are these pink dots. And the plus a halves, half of them go one way. Got my arrows this way. Half of them go that way. and the other half go that way. They're essentially being carried along by these vortices. That's really weird, yeah? That's a really cute state. And this is why we called it, oh no, this is just a movie showing the things, showing the vortex dynamics at the bottom. Sorry, the topological defect dynamics. Those green dots are the topological defects which are moving along this channel.
Those are simulations.
These are simulations, yeah. And we thought they would always be simulations. You couldn't believe anything like this would really happen, okay? So we'll look at the experiments in a minute, but first let's see why I called it a Cayley dance. All right, this is what I spent, when I was a student, I used to like dancing like this. And this is a Scottish dance, which is called Strip the Willow. And you can see that the ladies are doing things which look remarkably like these topological defects. And it's actually caught on. It's in all sorts of papers in the literature now. I feel a bit guilty, you know, because it's somehow if you say things slightly tongue-in-cheek if you're English, and if you're not English, people don't notice how tongue-in-cheek it is, and it gets used. Okay. Okay, so then we said, okay, so this is just summarizing where we're up to. This was the results of simulations, and they were careful simulations. We had to put in exactly the right number of defects so they'd fit the right number of vortices in the channel. All right, so they were, you know, they were simulated simulations. We didn't do reality here. So then we asked Francesc Sagües if he could look at experiments on these things. So now let me explain what the experiments give you and how we had to change the simulations to match the experiments better. But what you do get is very definitely Cayley dance-like patterns. So what they did is put, here we have a two-dimensional layer of this microtubule motor mixture. So this active stuff here is in a two-dimensional layer. And then they wanted to compare what was happening in channels of different widths. So what they put on top of it is something like this, a mask like this, so that there was a narrow channel, a wider channel, a much wider one, and so on. And they very carefully lowered that down so it was sitting on top of the microtubule motor mixture. And by doing that, the microtubules could sort of go underneath and fill up all the channels. And so they knew that they had the same activity, the same stuff in each of the channels of different widths. Note the channels are long and thin, but they do have ends to them. And so you're never going to get flow which is just, you can't just have flow like this. You have to have some sort of flow around the channels. So this is the nearest they got to a dancing state, and it's really pretty close. These are the topological defects. You can see that they're moving around each other on the vortices. Yep. But not in quite such a beautiful pattern as in the simulations. But you're definitely seeing the same sort of thing. This is where the defects are across the channel. These blue ones here are the -1/2 defects, which sit at the edge of the channel. And the green ones are the +1/2 defects, which are found all over the channel. The new thing is really that you get defects appearing at the walls. The defects tend to get created at the walls and then move into the center, and then they get destroyed at the other walls. In the simulations, we have conservation of defects. Here, it's much easier to create them and to destroy them again. And the reason for that is that the boundary conditions are much softer here. It's much easier for the microtubules to sort of move away from the walls and form defects, where in our simulations we had them fixed solidly to the walls. In a narrower channel, this is what happens. So this is a narrow channel where perhaps you'd expect laminar flow, or in this sort of geometry, just shear flow. Oops. This isn't going to play nicely. Let's see if I can do it. Okay, so let's start by where's my I wonder if it's going to be easier like that. Okay, so these are the simulations, in fact. What you see is you suddenly get loads of topological defects. I really wanted to play this one first, but I'm not sure it's going to do it. You suddenly get these defects appearing. You get shear flow, and then you suddenly get the defects appearing. Let's see if we can get the simulations to play, the experiments to play. Oh, what's wrong with it? Okay, there's the experiments. You get shear flow, and then suddenly it's disturbed by a load of topological defects here. The topological defects go away, and you're back to shear flow. And then you suddenly get these bursts of defects. And the reason is that the shear flow lines up the pneumatic. It lines up the microtubules. And we've said that microtubules don't like to be lined up. That's going to make them undergo an instability. They undergo an instability like this, and that's equivalent to them forming topological defects. So the basic idea is fine. The basic idea is fine. I don't think we want to do that. But the details weren't quite right in the original simulations. Slideshow. Slide. Okay, so I'm going to finish, because it's quite late, and I think we've probably done enough for today, just by some nice movies. Partly because I want to talk about these things a bit more tomorrow, and partly just for fun. These are again bacteria, but they're a bit different because they're crawling bacteria. These are Pseudomonas, and they crawl on the surface. Again, you can think of them as pneumatics because of their shape. And so you almost have to have topological defects in this system, okay? If you're going to have a pneumatic, at least locally, you can get topological defect-like configurations. And one of the stories I want to talk about tomorrow is whether these have any effect physically, and we're going to actually find that you get some physical things happening, biological things happening at those topological defects. And we might discuss also, are these going to be the same as what I've been talking about so far? Because these are systems with loads of friction and not much hydrodynamics, so why on earth should they be the same as the ones where you have swimmers with loads of hydrodynamics? I still don't know really the answer to that. This is some beautiful pictures from Aşkın Kokobas in Turkey. And this is a bacteria which divides and tends to stay in a straight line until there's a lot of stress. I'm not doing very well with my movies, am I? Should have made the effort to do a better job of, sorry about that, of going through them. There we go, I hope. Yep. All right, so it divides. Let's watch it divide. You get buckling, you get things which look very like these topological defect-like patterns, but probably the physics here, I'm not sure anyone really understands, but probably the physics here is more buckling, the sort of elastic transition where you take a beam and you push it and it zooms up. So this is beautiful pictures of his bacteria. And let me finish with this, which people tend to, is this going to work straight away? That's it, that's better. Okay, so this is another active system, which again, I know very little about. People are mucking around with sheep as well with these active systems, but my students like this movie. Yeah. Oh my gosh, it's still going. Yeah. Okay. So we've done 4, 5, and 6 today. The important thing, the real punchline, is that the new thing about active pneumatics is that you have these self-propelled topological defects which are created and destroyed. And what we're going to do tomorrow is just look at some examples. First of all, the story of the hare and the tortoise, which is topological defects in bacteria, and then look at eukaryotic cells, that's the squishy cells, and to try and see whether we can think about those as an active system. And that's 7 and 8 are very much ongoing research. Okay, thank you. Okay, anyone got any questions?
When you perform simulations, you have like a continuous model, like a deterministic model, right?
A continuous deterministic model, yes.
How things change when you consider stochastic models?
Not much at these length scales. If you want to look at, say, active particles, you can have MD-type models when they interact with each other. And then noise is going to be important, but don't think it's very important, actually, because the activity itself introduces quite a lot of noise. Ralph's much more an expert than I am about that. Might tell you I'm wrong. Yeah. Okay? The questions? No? Right. Okay, tea time. I mean, coffee time. It's tea time.